Greetings, minions. It has been snowy today, and frankly, I object to this. But that is okay. It didn't get too cold, so it's not accumulating. So I'll be okay. I will survive this one. But I'm very ready for winter to just be done. That would be nice. I don't know who I need to file a complaint with, so maybe I'll just shout out the window for a little bit. We'll see what happens. Hello. Yes, joining me today is Professor Percy, and she is trying her best to pretend I don't exist right now, doing a really good job. I was going to say she's going to be here for the stream and be much cuter than me, but, well, I'm on my own, so that's okay. Actually, going to take a moment and just let her out of the room. There we go. Alright. Because the last thing you want in a little study session is an angry cat who wants to leave the room and stop being any presence. So, yeah, aside from that, I don't have a whole lot else on my mind to talk about, so I'm just going to start doing some chemistry, and just so that I don't forget, hello, my name is Nathan. I've got most of a PhD, got a few months left to go, and I like talking about chemistry, so that's just kind of what I do. If anybody's got questions or anything, feel free to leave a comment, but otherwise, I'm just going to do some stuff and talk about it. So here we go. Okay, so last time we were doing an entirely different assignment. It was on special request from one of my tutoring students because they had an exam the following day. But the time before that, we were working on some of this stuff, so I want to keep going on that and finish it off before we move on to other things. So we talked about isomers, generating isomers, which have the same chemical formula but different connectivity. So I just kind of showed you what my method is for doing that. Just take the terminal carbon and just swap its place to this other one. Of course not to 5 because it's already connected there, but swap it onto a new carbon, and then keep doing that until you would make the same thing that you started with, or the same one as a different one that you have already made. Like if you move 6 to 3 and then 6 to 2, well, that is the exact same as when 6 is connected to 4. And so then you start with the new terminal carbon and start moving that onto other ones, and keep going until you can't. Alright. And then we're talking about systematic names. And so you start by identifying the longest or the principal carbon chain, and then that sets your numbering system, and then you figure out what substituents you have and what carbons they're attached to, and name them accordingly. And the ordering for that is alphabetical, based on the name of the substituent, not any prefixes like N for N-propyl here. And then, yeah, numbers and letters are separated by dashes, and sometimes, in the case of prefixes like N, you separate that from the chemical name by dashes as well. Multiple numbers in a row get commas. Of course, things like tri are a prefix, and so we don't name based on that. So I'll do one more of those. Because there's 3 of them left, but it does get a little on the repetitive side. Okay, so that's the wrong one, not marker. Pen. Okay. So we try some stuff out to try and find the longest continuous chain. So we go 1, 2, 3, 4, 5, 6, 7, and 8. So that, actually I'm pretty sure that is the longest chain. Yeah, first try. Look at me. Because this would be 1, 2, 3, 4, 5, 6, 7. And yeah, from carbon 6, all of these others have 2 more carbons. So yeah, that's it. Alright, so we've got, what I'm actually going to need to do is I'm going to need to make some room for myself. Okay. I'm not going to worry too much about that. Okay, so there's 8 carbons in the principal chain, so it's going to start with oct. Yep, make sure that's a T. And then the so all of the carbon bonds are single bonds, which is to say it's fully saturated. So it ends in ane, octane. And then figure out the substituents. So we've got a 3 carbon chain. So, and they're all in a row, so it's N-propyl. We've got a methyl, and we've got 1, 2 ethyl groups. So yeah, there we go. So we've got and to number these in to have these in the lowest order numbers that we can do. We got 1. We actually have to start counting from the other side. 5, 6, 7, and 8. So I make that change because this changes it from 4, 5, 6, 6 to 3, 3, 4, 5. So that is preferable. So we've got a propyl, we've got a methyl, and we've got a couple of ethyl. So ethyl comes first, and then methyl, and then propyl. So the methyls are 3, 3. Methyl is on carbon 4, and the N-propyl is on carbon 5. It's 5. So these are actually all just going to go in order. So yeah, I can do better than that. Maybe not. 3, 3, and because there's 2 ethyl groups, we call it diethyl because it needs a prefix to specify how many of them there are. So 3, 3 diethyl, 4 methyl, that's nice. 5 N-propyl, octane. I think that's bad. You should see my writing in person. Alright, so that's the whole procedure for something like this. With hydrocarbons, it's relatively simple because we don't have to deal with substituent priorities, which I'm sure we'll get there. Okay, so going in the other direction. So we're going to draw a molecule based on the name of it, and this is why naming is important in both directions. It has to be specific, so that when you have one structure corresponds to exactly one possible name. So how you approach these is start by looking up the length of the principal carbon chain. So this one is decane. That means it's got 10 carbons in a row. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Cheesiest of cakes. It is lovely to see you. Welcome back. How you doing? All right. So we got decane. So 10 carbons in a row, and all of them are single bonds because it's fully saturated. And then we all just you can kind of just attach the substituents in any order that you like. So this is 6 isopropyl, so it's 1, 2, 3, 4, 5, and this is carbon 6 here. So we're just going to put an isopropyl group on that. And so remember, back from talking about such things, I seem to have erased some of the important work, but so this is an isopropyl group. So it's basically just attaching to the middle of a 3-carbon chain instead of on the end. Doing great. Sped through physics today, got some cassettes and a vinyl. That's amazing. That sounds like a good day. How about you and your cats? I am doing just fine today. Had some tutoring this morning. That's the last tutoring I'll be doing this semester because everybody's exams are over now. So that went fine, and then got home, had some friends over for a bit, and yeah, it was a good day. And cats are doing just as floofy and lovely as always. Percy was around for a couple minutes at the beginning, well, maybe seconds, but she has since left us. They may show up, and they may not. What do the 2 numbers in front of it stand for? Right, talking about the 3-7 here. Because that is just specifying where the ethyl groups are, and I'll get to draw on that in just a minute. Yeah, it was a good day. Thanks for asking. It's been lovely, and now I get to do some chemistry, and that's kind of fun. Yeah, I'm definitely feel a little tired today, but so I might not go terribly long because my brain will fizzle out quick. But we're here for now. We'll have some good time. Also, cheesiest of cakes. I was hoping you were going to be back because I was doing some more thinking about that. Like when we were talking about the energy levels for an electron, and how when you're exciting the electrons with a certain source of light, it's the ground state that is mostly populated. So you came up with an analogy of run towards 1 and walk towards 3 being the different energy levels, and I think that's pretty good. I wasn't, because there was something that I was like, it's not quite there for me, and I thought of what it was. Run towards 1 and walk towards 3 sounds to me more descriptive of like a dynamic equilibrium, and so that's to say when you've got a reaction on one side and you have arrows like this one. So these arrows indicate that there's an equilibrium happening, which is, say, like there's A combining with B to form C and D, and that is happening simultaneously as C and D react to form A and B. So depending on the different rates of this reaction, like it might be a faster reaction for A and B to combine to form C and D than for C and D to combine to form B and A. And in that case, if A combining with B is faster, then you have an unequal. You draw the arrows so they're unequal to show that the forward reaction here is faster than the reverse reaction. So that's what was scratching at my brain when you said the walk towards 1, run towards 3. Other way around, walk towards 3, run towards 1. So I was thinking of like a little bit of a different analogy, and it gets a little strained, but here we go. So like the Boltzmann distribution, which is like that distribution of electrons that are in the ground state versus in the excited state, kind of more like Canadians. So even when we've got like a lot of excitement to travel, see what I did. Yeah, sorry, I'll go on. We've got a lot. If we have some excitement to travel, we got some motivation. Even if most people do end up traveling at some point, the number of Canadians traveling at any one time is very small. So the proportion of electrons that are in the excited state versus in the ground state is a really small proportion. and then so because like if and if somebody's traveling, like if somebody flies, from Toronto to London, almost all the time they're going to they're going to fly straight back to Canada. So going to go to one destination and come back to Canada, versus like it happens, but it's less frequent that someone flies from Toronto to London and then flies on to Tokyo. Let's where Japan is the land of ionization energies. So yeah, it's just it's a faster, more common. No, sorry, I said faster again, but anyways. So yeah, that's my very strained analogy. So now go back and read comments. That's so cool. Didn't realize that was a possibility. Tried to reevaluate in my head. Kind of thought of Minecraft, like it's both walking at the same speed. There's more force in the opposite direction, like when walking on honey in Minecraft. I like that a lot. I really do. I think that's a good way to think about it. And this is what I love. Like when people can like come up with their own analogies that make sense to them. I think that's the best way to learn, because the mnemonic that you'll know the best is the one that you come up with. And oh man, well you're so very welcome. I'm so enthusiastic about questions. And like when people are like really wanting to engage with the material. So I super appreciate questions and your thoughts about this. So that's awesome. I am like I said, I am always willing to be like distracted and talk about something, because like and like even if I don't know things off the top of my head, which I promise you I won't know everything off the top of my head. Like I will spend the time to track it down and think about it, but yeah, no, that was a lot of fun. It was a really, really good mental exercise. I'm glad you asked the question. All right, so quickly getting back to this question. So we've got the decane in purple, we've got the isopropyl in the teal, and we're just gonna take that out so that the 3,7-diethyl can be in red. And so for that we count 1, 2, 3. So this is carbon 3, and so that's got an ethyl group, and so this is 3,7-diethyl. So what that means is, so diethyl means that there are two substituents attached to this carbon chain that are ethyl groups, and they are attached to carbon 3 and carbon 7. So the first one on carbon 3, and then the other one, you count 1, 2, 3, 4, 5, 6, carbon 7, and that has an ethyl group as well. And there you go. That's the whole thing. Okay, wait, so since C and D takes longer as a reaction, that's the one where all the electrons, or most, are. I do not think that is really the right spin to put on it, because A and B and C and D have completely equal numbers of electrons. Electrons aren't lost in this reaction. They don't come in from outside, because the only species present in solution, when like if you've got a beaker of A and a beaker of B, and you pour them together into a flask. Now all you've got in there is A and B, which is they all these different molecules have their electrons, and they're just there. And C and D will always have the same number of electrons, as long as you're specifying all of the species that are present on the reactant side and the product side. Then you must have equal amounts of electrons and need all the elements. So this is so this is something that I think I can wrap and talk about for a bit, or in the area of it. So like C and D is located at the ground level. So you may be thinking of like the energies of compounds, because one thing that you'll see a lot of in chemistry is, so there's just like a graph where on the y-axis you've got energy, So higher energy as you go further on the y-axis, and then on the x-axis you've got time, which is like it's often in chemistry we won't call this time, we'll call this reaction coordinate, which just means the kind of like monitoring the progress of a reaction as it goes forward, which does happen in time, so that's why I'm going to call it time. But it's not the normal convention used, but it will do. So when a reaction starts, so we've got over here this here is the energy, like the total combined energy of A and B. So it's like all the energy that's in the bonds in the molecules of A and B, and all the energy from the movement of the molecules, the kinetic energy. So all that stuff combines to be just like very hand wavy, the energy of the system. So when these combine, there's as A and B get closer to each other and start to interact and react with each other, the energy goes up and reaches a peak and then comes down again. And this peak is called the transition state. And so this is just a state where they're coming together, they're experiencing electron repulsion, and they have to, hello, sweetie, little Daphne's come to get to be a little cutie. So this is a point where there's like if A and B are reacting together, then there's bonds being broken, there's bonds being formed. And all of that stuff is contributing to like a higher energy state of the solution as a whole. And then once it gets past that, it climbs that hill, then it's a downhill reaction to forming C and D. And these graphs can show a lot of different outcomes, like where C and D is lower in energy than A and B. It can have ones where C and D is higher in energy or the same energy, and we can use things like catalysts to modify like how big of an energy hill there is to overcome for this reaction to go forward. So is the second low point lower than the initial because of heat loss? Yes, it absolutely is. That is an incredible observation. Yes. So yeah, this is depicting this is the reaction diagram for an exothermic process, because the products in this case are lower energy than the reactants were. Sorry, sweetie. So that energy goes somewhere, yeah, like that's heat produced. Is like that for all chemical reactions. Yeah, it is. Yeah, that's just you nailed it. Absolutely. Right? Yeah. No. It's really cool how this stuff works, and like this is how we can tell if so there's a couple competing factors. So there's the this kind of energy difference between the reactants and the products. So this is like kind of providing the motivation for this reaction to go forward. And so this may be a spontaneous process. So you just pour A and B together, and they just start reacting. So there's like in order for them to get over this barrier, like if hi, you're very cute. So like if A and B are in the same place but they're not reacting, it might be that this energy the energy to get to the transition state. It may be that's too high of an energy for A and B to react. So they don't react to form C and D because they just can't get over that activation energy, it's called. But the like one way that you can overcome that is by heating the solution. So that you raise the energy in the system by adding heat. And then once you do that enough to get this over the activation energy, then you can release all that heat and it becomes exothermic there. Wait, is also vice versa, like the arrows where the C and D has to travel to the A and B on a reaction occurrence scale, since time can't travel back. Okay, yes. Oh my god, like yes. I love everything about where your mind is going, because this process is happening in reverse because we're talking about an equilibrium here. So yes, like C and D can react together and go back over that activation energy and return to A and B. But the like this is why we usually use the convention of not time but a reaction coordinate, because time can't go backwards, but you know, having a reaction coordinate just says like where we are on this scale. So we kind of free ourselves from the constraint of using time on the x-axis. So does heat speed it up because the molecules move faster, or the atoms? I forgot what each we use for explanations. Okay, so the temperature of a solution, or the temperature of anything, you know, the temperature of, you know, the gas between my hands, is a measure of the average speed of the molecules. They actually do a mathematical operation to it called the root mean square speed, but it's complicated mathy stuff that I don't understand super well. But basically, you know, temperature is an average of the speed of molecules running around, but it's not just related to speed. It's also related to collisions between molecules, like density of molecules, because they can transfer kinetic energy, and those are not perfectly efficient processes. So heat is released or transferred. I should say when collisions happen. So it's temperature the cause of heat. So kind of the other way around. Because heat is just kind of like measured in units of energy. So like heat is transferred in joules, just like certain like photons of a certain frequency have an energy in joules. So heat is energy transfer, but temperature is kind of a consequence of heat, because like because it is a measure of the energy of a system based on the kinetic energy and interactions between molecules. Does that kind of make sense? Because that felt like a lot of words. But but to answer the second part of your question there, so yeah, temperature and heat are different things. Nice, awesome. That's a really good start. Yeah, no, it was in like, you know, the second half of the first year of university that they actually went over that and explained it to us. So yeah, I figured you're doing pretty good. I guess the one thing I'll say is that based on, so I want to point out that so this graph would kind of be representative of a different set of arrows. So this would be no, that's the same arrows. Nope, never mind. I'm just a very silly person. Uh, okay, so um, so I just want to point out that there are other factors than just the energy of the transition state in determining the speed of a reaction, but it's very frequently correlated. So it's most of the time if something has a lower activation energy, which I should say is do, 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 do. So so this is the activation energy, the energy between the kind of the before state and the transition state. So reactions with a lower activation energy will very much most of the time be faster than reactions with a higher activation energy. So in this reaction, so A and B have a lower barrier to get over than C and D do. Like I'm just drawing lines and making things messy here. Yeah, so the activation energy for A and B is quite a bit smaller than the activation energy for C and D, and that is one way to get to this kind of consequence in the equilibrium. So the A and B reaction will be faster than the C and D reaction. All right. All right. What a lovely diversion. I really like going down little rabbit trails and just like talking about something topical. I like that more than going over questions. Anyways, so does it require more activation energy because of the loss in heat, or is it because the actual values of C and D themselves? That's a really cool question. Let me think for a minute. So it is endothermic. So there is. I don't want to say heat lost exactly. There's more. So going from C and D to A and B, there's more heat input than there is output, right? Because in this direction, going up the energy hill, like C and D are effectively like absorbing heat from the system in order to break bonds, rearrange bonds, and do whatever they're doing. So that energy is greater than the energy on the other side of the hill, and it's because that's the state where heat is being released. Bonds are forming and releasing energy. In this case, like on the far side of the hill, and so yeah, so there's so there so that makes it endothermic. That means overall the reaction going from C and D to A and B absorbs energy, so its surroundings will get colder. But I would not say I would say kind of the other way around. Like it doesn't need more activation energy because it loses heat, but the fact that it has a higher activation energy means that it absorbs heat overall. That the temperature of the system gets lower because of this reaction. Does that make sense? Like a closed system. Yeah. You could definitely think about it like that. If you think about it in a closed system, then you're getting closer to like the real like theoretical backing of this. That like the activation energy and the heat are related, but not like causal. If that makes sense. So yeah. Okay, cool. That's what, if you got 40% of it, that's genuinely pretty good. Like I tell my tutoring students very frequently, like, I do not expect you to remember everything we've gone over. Like that is a completely unrealistic expectation. like hopefully when we go over stuff and like revisit it the next week, like hopefully it comes back quicker on review. But certainly like my expectation is never that everybody like gets it right away, because this is chemistry is so much a process of learning. It's not just you hear it once and you get it, like that just that would be remarkable. I forgot if 3 or 1 were the ground level. Oh, no worries. I mean, in that example, 1 was the ground level and 3 was the excited state. But yeah, it's all good. And hey, I put all of these videos up on my YouTube channels of the same name. So if I'm just saying, it's there if you ever can't remember what we talked about and want to go back to it. Yeah. Hell yeah. Appreciate that very much. Yeah, and at some point, I will have the time and energy to go through those videos and like clip out sections where I'm like talking about some specific topic. Thank you so much. I appreciate that. So yeah, I'll get these videos split up at some point into little topics. I might do longer videos on that at some point, but at the moment I'm just kind of screwing around when doing this, and I'm also terribly busy otherwise. But one day my hyperfixation is going to land on video editing, and we'll get there. Okay, so we'll just do this one real quick. So going from a systematic name to a structure. Again, the first thing you're going to do is find the length of the carbon chain, and this one is non, and a nonane is a 9-membered carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. It has the suffix ane, so that means these are all carbon-carbon single bonds. It is fully saturated, and now it's got a 5 propyl group. So I'll go 1, 2, 3, 4, 5, and that's going to be our. Going to do it like this because that's not isopropyl. I was just going off the other one. Yeah. So they did not specify N-propyl, and so like it's pretty okay. It's a little more correct to specify the N, but if you just if it's just propyl, then it's just assumed that we're talking about just a straight hydrocarbon chain. So, and then we're going to do the 2268 tetramethyl. So tetra being the prefix for 4, means that there are 4 methyl groups. 2 of them are located on carbon 2, 1 on carbon 6, and 1 on carbon 8. So we'll just go around and find those. So this is going to be 2. Yeah, 1, 2, 3, 4, 5. Yeah, we started counting from this end. So we got 2. 6 is going to be this one. And 8 is over here. So we just go 1 and 2 methyl groups there, 1 methyl group there, and 1 methyl group there. And we're done. Kind of a lot easier to go from name to structure, if I am to be asked and believed. Okay. All right. Process of writing out the numericals reminds me of polyrhythms. I like that. So, and this is something I have no experience in. I shouldn't say none. I should say next to none. Because I'm not a super musically inclined person. I really like to sing. I've been doing like choirs and small groups since I was like 6. But I don't know a lot of music theory. Although I do find it terribly interesting when I get a little bit, because I took a couple music courses in university, like just very survey ones, not studying very seriously, but it was a lot of fun. And at the university, every for the one course at least, every Tuesday they do like a free kind of lunchtime concert where music majors come and just strut their stuff, or sometimes they'll have special guests come in if a professor is visiting from a different university, or a group is going on a tour. They'll sometimes come by for those things, and some really cool stuff that we got exposed to. And like there were some really good ones, like the opera workshop would come and do something from like La Traviata, which was just fantastic. A little musical nerd. I think one of my hyperfixations is avant-garde jazz fusion. That sounds really neat. I always enjoy jazz, and my little neurospicy brain really likes just songs where there's a lot of stuff going on, lots of little things to make my brain sparkle. Opera members are so talented. Yes, absolutely. I've been very lucky to see lots of their performances, and one of the coolest things I have ever done. So for a semester, I was part of a choir called Vox Musica. That was like I was taking it for partial credit, for course credit for my university, and so I got to sing with them. And they did this big Christmas program, and this is like a 60 or 80 person choir. It was pretty substantial, and we did a really cool Christmas musical from Carl Jenkins, I think his name was. Incredibly beautiful, like very like modern, with like some definitely some classical influence on the music, but pretty modern take on it. Really cool, really fun to sing, and then we did about half of the selections from Handel's Messiah. And just like I mean it's Handel's Messiah. It's incredibly epic music, and of course like we sang the Hallelujah chorus at the end, and also I forgot to mention, we're being accompanied by by an orchestra, and like just absolutely one of the coolest things I've ever done. It was so incredibly epic, and I don't expect to top that. But yeah, like singing the Hallelujah chorus in like a big church with good acoustics and an orchestra accompanying. that was something. Soft Machine. I don't know what this is, but I'm gonna find out. Jake sounds so familiar. He's from Soft Machine. He's also a great band. I love Frank Zappa, King Crimson. Excellent. I did not realize that Jenkins was part of was part of a group. No, that's really cool. No, please don't be sorry. Like this is like, yeah, my focus on this channel is kind of chemistry because that's what I'm good at. But this is also just like come and talk about cool stuff. I am always willing to be distracted and taken down some rabbit trails. And I've got lots of interests besides chemistry. Like sometimes I guarantee I'll be talking about some like astronomy, because I love black holes and like ideas about dark matter, and like I squealed like a schoolgirl when a few years ago the LIGO experiment detected gravitational waves from a black hole merger. Like, it is one of the most mind-blowing things. I cannot believe it happened in my lifetime. Very incredibly cool. Black holes are red. I love pulsars. Yes. They're all incredibly neat. About LIGO Lab, about pulsars. Yes. And about things like collision of neutron stars. Oh, so there's this. No, sorry. Brain just go. But the LIGO observations, it was one of the subsequent observations from LIGO, because of course it's continued to pick up really cool things. So there was an experiment where I believe is a collision of neutron stars, and it was detected by LIGO, and then LIGO sends out this alert to astronomers across the globe, like, look at this part of the sky because something cool is happening. And I think it was a neutron star merger. I could be wrong on what the event was, but it was incredibly cool, because that proves that gravity, or that light, yeah, no, sorry, gravitational waves travel at the speed of light, which is mind-boggling and super super important to our model of physics. Okay, about pulsars, the one that they proved Einstein's theory or something similar. Right? Maybe it was a clickbait article. I'm not sure which of Einstein's theory that may have proved. It very well may have. Like, a lot of of Einstein's theory are like still being like tested and proven correct, as we get better and better instrumentation. Was the one that chose one of the pipe things rather than other. So that sounds like wave particle duality. And about like the electron diffraction experiments. So there's two slits, and you fire a beam of electrons at these slits, and depending on whether you are, cameras as like depending on whether there's like some observation of the slits themselves to see if the like it's like sorry, if you're observing one of the slits to see if electrons are passing through it, then they will act like particles. But if you don't measure that, then they will act like waves and form a diffraction pattern. So by manipulating the level of observation of this reaction, you either get two bars straight in front of the slits where the electrons have essentially like acted like particles, or you get a diffraction pattern, which proves that they act like waves. And like it's and like it's wild and it's weird and it makes no sense to our simple little ape brains. But the universe is under no obligation to make sense to us. But it isn't magical either, because like it's the observation of this one place where like you're looking for electrons that like once it interacts with the the thing doing the detecting, the wave function of the electron collapses into a single point. And so it is like now the electron is there because it has encountered this thing which interacts with the wave function of the electron, instead of continuing to act like a wave, and going on to go through both slits and diffract with itself. Whew. Science is neat. Least ways I think so. Is it because it's like frames per second that we can see, like we move our hands fast, it looks like a wave of flesh, but still a second? No, this is a different phenomenon from that. Yeah, I like how you phrased it there. Our retinas, as far as I'm aware, work a little bit differently from like an electronic detector or screen, because like those have a certain like refresh rate where the cells are like it depends. It might be light emitting diodes versus liquid crystal displays versus cathode ray tubes. All have different mechanisms of refreshing the image, and so they have different rates of doing that, and that's what causes frame rate. So like your monitor has a certain rate at which it can refresh the pixels, and you'll display different patterns of light. So it's a purely like electronic on-off binary system that produces things like frame rates, and our eyes, our retinas, don't operate on that same principle. So it's a little bit different than that, but when you're doing some of that in front of your eyes, and you see like the kind of blurry, like the blur, the motion blur, that is because of the processing speed of our brains. As far as anybody, please feel, anybody who knows more about this, like, please feel free to correct me, because I'm always willing to defer to greater expertise than my own, which is a bar that is planted firmly on the floor. Yeah, so despite knowing little to nothing about it, it's so cool to talk about pulsars. Yes, absolutely. Pulsars are phenomenally cool things. So pulsars are so those are neutron stars. Which are another thing that I really like, and I know some things about it, and so we're just info dumping about this now. This is thirsty work. Okay, good break. So yeah, neutron stars are these collapsed cores of supermassive stars that go supernova, and depending on the mass of the star and the density of the core when it goes supernova, because that can change based on the elemental makeup of the sun and of the core, because it may have heavier elements and so a denser core. So if it has a sufficiently dense core, then upon a supernova, it will compress that as the star explodes. It compresses that center, and if it is sufficiently massive, it'll form a black hole. And if it is not quite that massive, it'll form a neutron star, which is a wild thing, because it's just like this neutron soup, where like there's no like the gotta try and think about what the correct things to say about this are. Black holes in utero. I like that. This is like just a little baby ones, almost black holes, but not quite. But yeah. What was I saying? Right. Yes, neutron stars. Yeah, so that's the stuff where it's like we can see these, and like if you took a teaspoon of it, of that material, it would weigh approximately like the same as like half a mountain. That's the kind of densities that we're dealing with, because we don't have a whole lot of that electromagnetic repulsion. Like you cram a bunch of protons together, and that's putting all these electrical charges in the same place, and they're the same charges, so they want to repel each other, and that gets worse and worse and worse as you pack in more and more protons, which is why like really massive elements just tend to break down, because there's just so much force trying to pull it apart. But neutrons don't have that issue, because they are neutral, or but aren't photons massless? Yes, photons are, yes. Neutrons are very not. If we're still talking about neutrons, if you're, because I'm not sure which photons you're meaning, but yeah, the neutrons in a neutron star don't have that electromagnetic repulsion, and they cluster very hard, and then they're nuclear, because they don't have an overall electrical charge. That's all good, no worries. So they don't have an overall electrical charge, but they do have a small magnetic moment. So technically, they do, by nature of that, have an electrical charge, because the electric force and magnetic force are coupled, as they say. You can't have one without the other. But It's not the extent of like proton-proton repulsion that you would get in just a normal atom with protons. So all of these these small, tiny little magnetic fields in these neutrons align with each other, and so they become extremely powerful, like just completely unthinkable amounts of magnetic power, just pulsing off of these things, and that superheats anything in proximity to the neutron star, and can cause these like jets of radiation driven by the magnetic fields, because there's these just magnetic basically vortexes that so it just sends these beams of radiation just shooting out of the poles of a neutron star. And oh man, and the coolest thing about pulsars is how fast they can spin, because it's crazy. Because some of these pulsars are rotating hundreds of times a second, or they'll have I'm not exactly sure what the pulsar rotation speed. So the fastest pulsar, 716 times per second. And I need you to understand how insane this is, because so neutron stars are usually about 10 kilometers in diameter, so about 35 kilometers in circumference, and that is spinning 716 times per second. These things are spinning at speeds where you can't do Newtonian physics on them, because they're going so fast that you have to apply relativistic effects from Einstein's theories. It's just the speed, the energy of these things is mind-boggling, truly mind-boggling. Okay, so now go to read back on your comments. Where's I am lost. Yeah, they radiate like a lighthouse. Yeah, exactly. Yeah, it's just on perfectly opposite poles from each other. Yeah, no, that's very. I feel like I can't really comprehend that, because that's a significant portion of the speed of light. Like we're talking about if we're talking about one that's about that is the entirely wrong thing to. Yes, thank you. Much better. So we're talking about 716 times per second, and every iteration of that, it's going, for a 10-kilometer radius neutron star. Let's say it's going, about 31.4. Well, yeah, because it would be 10 times. Yeah, so 10 times pi. No, I'm just. Pi d. Yeah, I can do math. Really, I can. 3.14. So basically, that many kilometers every time it spins, and it spins 716 times a second, means it is going 22,500 kilometers per second, which is crazy, because the speed of light is 300,000. So this is like 1/12 of the speed of light, which is bonkers, completely crazy. Yeah. Wild stuff. No, go away. Nobody likes you, Outlook. Okay. Yeah, where's my... I think I closed my whiteboard, but that's okay. I'm not using it very much. My favorite courses that I took in my undergraduate was absolutely for sure the astronomy courses, because I find astronomy is just completely mind blowing, and just very, very cool. I was genuinely thinking about changing my major to astronomy because I liked it so much, but then I realized that's just a lot of math and staring at squiggles on a screen all day, and instead of that I can go into a lab and blow things up. 12th is even more insane, and the way we just passively encounter that so constantly. Yeah. Oh yeah, no, the universe is genuinely such a scary, crazy place, and we're so lucky here that we're just like in this nondescript corner of a nondescript galaxy, where like there's no. Yeah, there's no exploding stars in our immediate vicinity. There's no pulsars that are baking the crust of the Earth. Like we're fortunate to have been safe for a couple billion years here. Arson is fire. Yes. Oh, I should. Okay, so now I'm gonna tell the story of when I turned a flask into a flamethrower because at this point I feel like my brain is a little fried and doing chemistry is hard, so I'm just going to talk about what I feel like. And so this one time, um, it was in the summer, and I was probably in my first year of grad school, so um, I was sorry, I'm very distracted by this. Just one there. So yeah, I was smart enough to know what a fun thing to do would be, and dumb enough to do it. And so I was destroying some drying agent. So we've got all these solvent stills in our lab because we have to. Yeah, absolutely right. So we got these solvent stills that we use to remove water from other solvents, other solvents like hexane, like hydrocarbon solvents, petroleum-based solvents, things like that. And when we're doing a reaction that water could really mess with this or react with something that we don't want it to, which is often in my kind of chemistry. So we have to use these solvents that have been dried. So we put them in a sealed flask under pure nitrogen gas, so no oxygen gets in, and it's perfectly dry air. There's no water in it, and so we seal it in this flask with a condenser on top, and then we put it over a drying agent, just something that reacts very aggressively with water. So things like sodium metal. It's really fun, let me tell you, to take a chunk of metal, of sodium, and take like a butter knife and cut it. It's a weird experience. Highly recommend. It was kind of neat. So took some of this sodium metal, put it into a little a ribbon press. So like this big lever presses it down through an extruder, where you get just this really, really, really thin ribbon of sodium metal. And so you put that under this solvent that you want to dry. And sodium reacts very, very vigorously with water. Like you've probably seen people like on YouTube or some people throw a chunk of sodium into like a lake or something, and it explodes. And that really happens, and it's very, very fun, as long as it is done in a safe and responsible manner by trained experts. Just wanted to point that out. So, the reason that it explodes is because sodium just has this one valence electron, and this valence electron is really far away from the nucleus, and so it's really easy for sodium to give it away. You hope to be a trained expert someday? Oh my god, that would be so cool. It's a pretty fun time, I gotta tell you. I think that is incredibly cool. Okay, so yeah, sodium reacts with water to produce H2 gas plus sodium hydroxide. So just a strong base. This is one way that you can make just a sodium hydroxide. I wouldn't do it this way, to be clear. There's safer ways to do that. Plus 2H2O. And just go going to balance reactions because I could not deal with leaving it unbalanced. Okay, so so when sodium reacts with water, you get this base, sodium hydroxide, and you also get hydrogen gas. And you may remember some of hydrogen gas's greatest hits, such as the Hindenburg. It's extremely flammable, and in sufficient concentration, it is explosively so. So it explodes because the electron is far away from the nucleus when it breaks. No, not quite. So it reacts with the water because of that reason, because the electron far away from the nucleus, it very much prefers to not be on the sodium. Because it experiences what's called a low effective nuclear charge, which is just like how strongly the protons are holding on to that electron. It's very weak for sodium, so that electron can easily be taken by something else. So water, specifically the hydrogen on water, is very reactive with that. It will take that electron very happily and form molecules of hydrogen gas. The reason that it explodes is because when you get enough hydrogen gas produced, the other thing that this produces is heat. So often you'll just see this triangle used to depict like this is heat, because it's just the Greek letter delta. Don't worry about it too much. This means that this reaction produces hydrogen gas, sodium hydroxide, and heat. A lot of heat. And when you mix heat with an explosive gas, boom. So that's why it explodes. It's the combination of heat released and the hydrogen gas, the flammable explosive gas. Yeah, exactly. Yeah. So I was using a different drying agent. It's called lithium aluminum hydride. LiAlH4. Delta, both change in and heat. Yes. It does mean both of those things. And so you will often in chemistry see delta used as change, and you will often see it used as heat. This is just kind of like, it's almost like a colloquial use of delta to mean heat, because it's just meaning mostly just like change in energy. So it's just kind of become common to describe heat as this. But specifically, it's like delta just on its own means heat. So that's where we kind of like justify to ourselves, hey, this isn't a completely stupid way to depict this. That's how we justify it to ourselves. So, okay, so this lithium aluminum hydride is the drying agent that I was using, and it essentially does the same thing as sodium. It creates hydrogen gas and a lot of heat. But unlike sodium, it's just this nondescript gray powder. And you can't tell just by looking at it if this lithium aluminum hydride is active or if it's dead. If it's just like slowly reacted with like water in the air or other stuff and just like old and gone off. Is it because value of heat equals change in energy or total energy? Yep. Exactly. Just like we were talking about over here with this reaction diagram, which has gotten very messy, but we're just going to go with it. The change in energy is a change in heat. It's a transfer of energy, because that's all energy. That's all heat is a transfer of energy. So yeah, very, very much that the value of heat means a change in energy. Yeah, absolutely right. Okay, so the way that we usually and always should destroy this drying agent is you react it with ice cold. Not even ethanol usually. Propanol. So that's just carbon, 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 OH. And then these are H3, H, and H3. Like propane. Yeah. So this is like propane, but with a hydroxyl group on it, and that makes it an alcohol. And isopropanol is rubbing alcohol. Like you can buy it at the drugstore, it's actually a really good solvent for a lot of things. But yeah, it is it is an alcohol that's based on a propane group. So alcohols and water are really similar in a lot of ways. So like this is water, and this is like an alcohol. This is this one is methanol. But like this group and this group are exactly the same. They and so there, like, of course there's most definitely differences between water and alcohol. Lots of different properties, but the key functionality of water and alcohol is very similar. Also, is rubbing alcohol in labs different than in stores because the additives they enforce from prohibition, like added wood alcohols? Yeah, that's. Your questions are fantastic. I love this. So yes, in research labs, we can get large quantities of it's actually just ethanol that we can get pure. So isopropanol or like rubbing alcohol in the drugstore is exactly the same as we get in the lab, because because it's poisonous in any form. Like you don't need to treat it with anything in order to make propanol poisonous. So I just man, never stop asking questions. This is like I could not be like more excited to have you here and have all your questions. It's wonderful. Yeah, for rubbing alcohol specifically, you don't need to add anything to it to make it poisonous. It's ethanol. That was the big thing, because like that's the stuff that's in beer and liquor and all stuff. That's the stuff that you drink and it makes you drunk, but it doesn't kill you unless you have a lot of it. So technically, it is poisonous in certain amounts, but so is everything, mind you. Are they available to the public, or is it like Breaking Bad where they put you on a list? So when you're at a research institution and you order pure ethanol, or like 95% ethanol with no additives, no bitterants that they put in it. Because you're right, rubbing alcohol. So I should go back, because I realize I've made a miscategorization. So rubbing alcohol. When it's called rubbing alcohol, it can either be isopropanol, or it can be ethanol, like high concentrated, like 70 or 95% ethanol, plus bitterants, and they do that to make it poisonous, so that people will not drink it. Do you need to be 21 and up to get the pure ethanol? No, and I'll tell you why in a sec. So yeah, rubbing alcohol, that's my mistake. I miscategorized it a bit. So it doesn't just mean isopropanol. It can also be ethanol plus poison. But yeah, so to order pure ethanol, 70, 95, 99% called anhydrous ethanol, you do get put on a list. But that's like you are a part of a verified research group, and you log. You have to fill out forms whenever you take this out of chemical stores, and track the use of ethanol because of those reasons. Because this is not for consumption, and if people were to say there'd be big problems and huge regulatory issues around having that much essentially drinkable alcohol. So you don't need to be 21, because you just need to be ordering this like on the authority of your research lab. And so like I'm in Canada, so drinking age is 18. So everybody who's working in a research lab, at the university level is going to be 18, so legal drinking age, all that stuff. Yeah. And so here's another fun little fact. So methanol is wood alcohol. So this stuff here with just a methyl group attached to a hydroxyl. So methanol is quite toxic. Like this will kill you. But first it'll make you go blind. Sorry, that's not actually important. Well, it's fun, but anyways. So if you get methanol poisoning, which can happen through like moonshine. A lot of moonshine is contaminated with methanol because you have to be very, very careful when you're distilling it to just get ethanol. And you usually want to at least double distill it because methanol can distill at the same time as ethanol. You can get contamination, and then your alcohol is poisonous if you've made moonshine. Methanol poisoning, very serious and quite common. So if you get methanol poisoning, which say if not you, but the proverbial, the royal you, if you get methanol poisoning, you'll start to lose your sight because it attacks those first before it otherwise kills you. But the antidote is ethanol. And so, like, if you get methanol poisoning, just get a better source of alcohol and drink as much ethanol as you can handle, because that will kill you less. And the reason that it does this is when it gets to your liver, alcohols meet an enzyme called alcohol dehydrogenase that turns it into I believe aldehydes. It changes an alcohol into an aldehyde or a ketone depending on what the alcohol was. And so in the case of methanol, that would be forming formaldehyde, which is highly toxic and difficult for the body to process and run through. Oh man. Okay. Yeah, I'm gonna answer that question after, because that's an interesting question too. So yeah, methanol, when it hits the liver, will form formaldehyde, and that stuff will kill you. But ethanol forms ethaldehyde or acetaldehyde. Both of those are technically correct names. It's fine. And that is much easier for your body to process and eliminate. So by flooding your system with ethanol, you kind of outcompete the methanol for this enzyme, this alcohol dehydrogenase, and so it processes that into ethaldehyde, which is easily eliminated. And in the meantime, the methanol just gets expelled from your system because it goes through the liver and didn't have time to react with the enzyme. Wait, so if you died of methanol poisoning, does your corpse stay preserved? What a wonderful! I love this so much. What a good question. No, the answer is no, because the amount of formaldehyde you need to preserve an entire body is huge. It's a lot. It's really you basically like flood, like submerge the system in formaldehyde, and that's how you preserve things, because it keeps like oxidants and stuff away from whatever you're preserving through it. Okay, so how do you get methanol poisoning from alcohol? Oh, why is this chat so hard? Sorry, I've got this little box on mine. If you methanol poisoning, if moonshine is from bananas, so moonshine can be from all sorts of different sources. Because all moonshine is like, if you take like almost any fruit, like any source of sugar, and then let that ferment, that will form alcohols. But the thing is, you don't just form ethanol. You form mostly ethanol, but not entirely. You'll like in the fermentation process, you'll pretty much always get a substantial portion of methanol with your ethanol, and you'll get other alcohols as well. You can get propanol, you can get butanols, and other things. So there's a mixture of different alcohols that you get from fermentation processes, and you distill them at different temperatures in order to separate them. And so that's how. Methanol is called wood alcohol because that was a very common source of methanol once upon a time. Now we get it from other sources. I believe we just do the catalytic dehydrogenation of methane. Say that 5 times fast. So we have different sources for methanol now, generally that don't involve distilling, like the sap from wood and stuff. Yeah, okay. Oh, right, because I was going to say, like ethanol, the kind of like common name for ethanol used to be grain alcohol, because that's what you would distill from grain. And it's just different compounds in the in the sugars and in the source material form different proportions of methanol, ethanol, etc. Just an association, well, I forgot the term. So it's just kind of like an old name, an archaic way to name it. Like using the crown to refer to royalty type of thing. Pretty much. It's just an old way of referring to these things. And there's lots and lots and lots of those in chemistry. We use a lot of pretty archaic terms. Because it's run by a bunch of old white men who don't update things fast. Whew. That was really cool. I love talking about this. Oh, so I was for a bunch of years I worked with Let's Talk Science. It's a volunteer organization that we like go to schools or bring kids in and just do science with them. My favorite experiment to do with kids, it was like grade 12, grade 11 and grade 12, I think we led into this experiment, because it was a fuel efficiency lab. And so we had 4 different alcohols. We had methanol, ethanol, propanol, and butanol. And you take these and you take the mass of alcohol that you start with, and then you put this in a container with a wick, and so you light the wick and it burns the alcohol, and just like keeps sucking up the alcohol and burning that for combustion, and you use that to heat water in a beaker. And so by measuring the change in mass of the alcohol, like how much you have burnt up and like combusted. You take the change in mass of the alcohol and the change in temperature of the water to see like how much of this alcohol do I have to burn to get this much energy out. Delta. Yes, exactly. Yeah, you measure the changes. Perfect. And so you get different fuel efficiencies, and alcohols with longer carbon chains, like the butanols, they contain more energy because they've got more bonds that break and more carbons to oxidize. So anyways, but the key thing here is that this is done in a high school classroom specifically in Alberta. And so of course I got the cheeky little questions from a student being like, oh man, what would happen if I drank this? And to that my response was, well, 3 of these alcohols will kill you, and I'm not telling you which one is safe. So, other than that, it's that's between you and your teacher. Do they last longer because of activation energy needed? No, not really. So, so let me show you what happens. So, when we have H3COH, delta. Morphisms, yeah, right. And I was like, please don't do that while we're in the classroom, because in here you're my responsibility. But like, if you take it out there, like, That's on you, man. Instead of pills, you get potentially fatal alcohols, right? And it's like, are you willing to take the risk? Because like, it's no skin off my back. Okay, so when you burn methanol, you're going to get CO2. Oh yeah, and I need O2 on this side because of course we need oxygen to do the oxidizing that produces a combustion reaction. So it's going to form CO2 and water. 1, 2, 3, 4. So it'll be 2 of these. I don't have the mental capacity to balance this right now, so I'm just going to leave it, even though it hurts my heart just a little bit, but it's fine. So basically, this produces, but the key here is there's 1 carbon over here, so there must, in a balanced reaction, there must be as many carbons on this side, on the product side, as there is on the reactant side. And so there's 1 carbon here to 1 molecule of CO2, and that releases a certain amount of energy. It takes a certain amount of energy to get going. Again, just like the energy diagram here, it takes a certain input of energy, but then it releases even more energy than that. So that's what's happening here too. This is what happens in all of these like self-sustaining combustion reactions, like when you're burning a log of wood, for example. So that's for methanol. So you get 1 molecule of carbon dioxide for every molecule of methanol that you combust. But now, if you've got something like ethanol, so you got this, that plus heat and oxygen, of course, is going to give off 2 molecules of CO2 and an unspecified amount of water, and then heat as well. But now, like we've got, in both cases, we've got 1 molecule of alcohol being oxidized, being combusted. But the top one only has 1 carbon, so it only produces 1 molecule of carbon dioxide, and this is the reaction that produces heat. Forming this carbon dioxide from the alcohol is producing heat. Same down here, but in this case, this 1 molecule of ethanol now contains more carbons, and so it can do this type of reaction twice. Now, it's not that ethanol is twice as efficient as methanol in terms of energy production, because the ethanol is also denser than methanol, because it's a more massive molecule fitting into a very similar amount of space. So it's not a 1-to-1 change, but in general, this one reaction, this reaction with 1 molecule of alcohol produces more heat than with methanol, and that trend continues all the way to butanols, C4H10O. So that's just the formula for butanol that would have 4 carbons, and you would get 4 molecules of carbon dioxide out of this, and so on and so forth. Yeah. Okay, so I'll finish off my story about making a flask into a flamethrower. Right, this is how we got onto this subject. So, in order to safely destroy these drying agents they'd really like to explode. So basically what we do is we try to slow down the reaction so that you're still producing hydrogen gas and heat, but you're producing it slower. And so you're absolutely love story time. So when you're producing heat, it's got time for that heat to kind of dissipate and spread out, instead of just like being a really, really fast reaction making a lot of heat all at once. So we take, so the steps is you take isopropanol and pour it into a big flask, and then you put it on ice and you wait for it to get really cold, because again, the thing that we really want to avoid is fast buildup of heat. So we we get the alcohol really cold and react it that way. And so because alcohol is similar to water in this way, it's got that proton that can react, form the H2 gas with your drying agent, but when it's an alcohol instead of water, it's a slower reaction. So it takes more time to do this reaction, and so the time in which you're producing that heat is kind of spread out, and you're keeping it ice cold, and so that's how we keep this safe. So that's how you're supposed to do it. But again, I was quite smart and very stupid. So I thought, well, I bet you it would be more fun though if we just take a little bit of nice room temperature water and just drip a little bit of that into the glass. Just see what happens. And for a moment, I was really disappointed because I took a little pipette and dropped two tiny little drops of water, like really small drops, but just dripped onto the surface of this gray powder, and nothing happened. The powder kind of like up over the surface of the water, of the drop of water, but nothing really happened. It just looked like slightly wet powder, and so I was getting a little bit disappointed. But then I saw it start to glow, and like glowing red hot, because like it's reacting very fast, and producing a lot of heat. So this powder started to glow because it was just an ember at that point, and a second later it just like just flames started shooting out the mouth of this flask, and I'm just standing there, probably cackling like a madman, but having the time of my life. And because I'm good at what I do, and I am a trained expert, and nobody should reproduce this, things were fine. Like the flask didn't break. It was all done like in a fume hood. It was about as safe as it could be when you're causing a controlled explosion in a glass container in your hands. Saying that out loud wasn't great, but yeah, it was very fun. That's a core memory for me. That pretty much describes a lot of chemistry. I'm scared of this, but it's fun as hell. So it was very sturdy glass, not as much as you might think, because so the flasks that we boil solvents in, that we make these solvent stills out of, is just so they're round bottom flasks, so like pretty close to spherical containers of glass, and they're very thin. The glass is really thin, and it's intentionally so because they get heated to really high temperatures, and so if you had thick glass, you're in danger of cracking the glass. And so by having thin glass, then the thermal expansion of the glass expands under heat. And if you have thick glass, then you have stuff on the edges getting really hot while the core of the glass is pretty cold, because glass is a good insulator, so it doesn't conduct heat very well, which is the other reason that we have thin glass, because we want to get the heat into the solvent. So yeah, the walls of these flasks are actually very thin. They're strong unless you hit them in just the wrong way. Yeah, fun but scary as hell was me during frog dissections. Joe, I did feel bad for the poor frogs. Fair enough. I never dissected a frog. I dissected a sheep's eyeball once, and that was mostly just gross. But yeah, it was fine. But yeah, I never have dissected frogs. Yeah, but yeah, it's weird as heck. But oh man. So yeah, that is my story of homemade flamethrower. Crucified one too. Oh, tastefully crucified frog. That's important. I'm glad that it was tastefully done. Oh, and absolutely fantastic. I love it. Because I mean, like, the frog doesn't mind. He's super dead, so that's pretty morally neutral there. So we're good. Oh boy. Oh man. Well, I gotta tell you, cheese and cakes. This is. Oh my god. Oh man. Oh god, I'm dying. Oh man, I just sign me up for Frog Jesus Church. Like I'm there. I am now deeply invested in this. Oh god. Oh yes. So, like as a general rule, I'm not going to talk a whole lot about religion on this channel, but sometimes we're going to talk about religion because like I was raised in a very like like very creepishly conservative Christian community. Like very like fundamentalist evangelical. I am now very much not that, and so my favorite all of my favorite jokes include just a bit of sacrilege at least. It's just yes, it's good. New comic book idea. I would read the crap out of that comic. I tell you. Oh man. That's, that has absolutely made my day. Oh man. We'll come back. We'll sing the praises of Frog Jesus one of these times. He was bit by radioactive high school dissector. I love it. I'm thoroughly invested in this. Let me know when the comic book comes out. I'll buy just a whole case of them. That's brilliant. Oh, but my friend, it has been absolutely lovely. I have thoroughly enjoyed this. Thank you so much for coming out again and asking all your questions. Just keep them coming. It's the absolute best. But my brain is super fried, and so I am going to call it a night here. But I hope you have a really lovely time, and I will. What is this? That sounds like a really weird thing. Okay. Yeah, I just thank you so much. I had a lot of fun. But yeah, no, it's super cool. I am always like very keen to talk about science and cause I'm a nerd and I love that for me. But yeah, I hope you have a lovely evening. I will be back on Friday, and if like no pressure, but if you can make it, then I'd love to see you again. But you have a great night, and I will talk to you later. Bye.